Okay, let's unpack this. Imagine if a foundational concept in modern physics, maybe one you learned about in high school, was actually, a point of deep disagreement for one of the greatest minds who helped invent quantum mechanics itself.
Right.
And what if his critical essay on it was so challenging, maybe so provocative, that it was later just deleted from a new edition of his own famous book?
Yeah, it makes you really stop and think, doesn't it?
It does. This isn't just some footnote. It feels like a bombshell, really. Makes you question how science actually moves forward.
Indeed. We're talking about Erwin Schrödinger, Nobel laureate, obviously famous for his wave equation, and, well, everyone knows the cat paradox, right?
Yeah, of course, the cat.
But today, our deep dive is taking us into a much lesser-known piece of his work, but honestly profoundly insightful. It's his 1950 essay, Are There Quantum Jumps?
And that title really says it all. Our mission today is to get into Schrödinger's, powerful critique of this whole idea of quantum jumps, those sudden instant changes atoms supposedly make between energy states.
He called his own view heretical.
Heretical. And as we'll see, he had some pretty compelling reasons for using that word.
Exactly. And our mission, it goes a bit beyond just dissecting the physics arguments.
Yeah.
We want to connect his thinking to these bigger philosophical questions about how science communicates, how knowledge evolves, and sometimes maybe how it even forgets its own roots.
Forgets where it came from.
Yes, historical context. This isn't just about physics. It's really about the nature of knowledge itself, how we build it, how we share it.
Okay, so to guide us, we're looking directly at excerpts from Are There Quantum Jumps, right? As it first showed up in his book, What is Life? And there's the related PDF that has the text, too.
That's right. And it's really key to remember, as you mentioned, this whole chapter was later removed from What is Life?
Which is just wild. It really tells you something about how uncomfortable his critique must have made people feel back then.
Definitely underscores the depth of the challenge he was posing.
Okay, so let's set the stage. Because Schrödinger doesn't just leap into the quantum stuff. He kicks off his essay with this really powerful quote from Galileo.
Galileo, someone who definitely knew about challenging the status quo.
Right. Galileo wrote, I began to believe that a man who gives up an opinion that he drank in with his mother's milk and that is accepted by people without number, to arrive at another that is accepted by very few and denied by all the schools, and that really seems a very great paradox, must necessarily be moved, not to say forced, by more effective reasons.
Wow. That quote, it just immediately sets the tone, doesn't it? It frames everything he's about to say.
Totally.
He's not just tweaking some technical detail. He's putting himself out there saying, look, I'm challenging scientific dogma here, almost like Galileo did.
Which makes you wonder, right, what were these effective reasons that could force someone like Schrödinger, a Nobel winner, a founder of the field, to challenge something so accepted?
Exactly. Think about the sheer psychological cost, maybe even the professional risk, for a scientist to question a theory that's been so successful, especially one they helped build.
Yeah, you'd have to be incredibly convinced, wouldn't you? Convinced that something was fundamentally off.
Extraordinary intellectual courage, really. A deep conviction.
And for Schrödinger, that courage wasn't just about the physics itself, but about tackling this deeper issue he saw. He called it the grave danger of physical science getting severed from its historical background.
Severed from its history. What did he mean by that exactly?
Well, he argued that the big innovations of the last, say, 50 years before he was writing, and he included his own work in this, mind you, were often overrated compared to the huge achievements of earlier centuries.
Overrated. Interesting.
Yeah, he thought this led to a disproportionate foreshortening of history. Like, we lose sight of the foundations everything rests on. It's like, we're ignoring the giants whose shoulders we're standing on.
And by doing that, we lose the context that actually gives modern science its meaning.
That's exactly his point. And he goes on to explain why this historical amnesia, this loss of context, is so dangerous.
Okay.
Schrödinger believed quite strongly that all science is bound up with human culture in general. Scientific findings, no matter how specialized they get, are ultimately meaningless outside their cultural context.
Meaningless, that's a strong word.
It is. He worried that if science becomes too isolated, understood only by this small group of close fellow travelers, like an exclusive club, it will eventually atrophy and ossify. It'll become rigid, lose its vitality, even if the internal jargon gets more and more complex.
So the idea is that when concepts get detached from their origins, the problems they were trying to solve, the assumptions they made, they can turn into dogmas. almost like superstitions.
Exactly. It's a really powerful warning about forgetting where ideas come from. He even quotes Benjamin Farrington to back this up.
Ah, Farrington on Greek science. Great stuff. What does he quote?
Farrington wrote, "History is the most fundamental science, for there is no human knowledge which cannot lose its scientific character when men forget the conditions under which it originated, the questions which it answered, and the functions it was created to serve."
Wow.
And then Farrington adds, "A great part of the mysticism and superstition of educated men consists of knowledge which has broken loose from its historical moorings."
Knowledge which has broken loose from its historical moorings. That phrase really sticks, leading to mysticism and superstition. It makes sense. If you don't know why we believe something or what its limits are, it just becomes this thing you accept without question.
Right. And Schrodinger even has this really unusual analogy for this trend towards deliberate obscurity in science. He calls it gongorism.
Gongorism. Never heard that one. What's the story there?
It's named after a 17th century Spanish poet, Luis de Góngora. Apparently, his style involved using acuity and skill on making it as difficult as possible for the reader to unravel the sense.
Huh. So intentionally hard to understand.
Exactly. Schrodinger says the poems might sound good, maybe make some sense, but you need extended commentaries to grasp the meaning safely. It's like an intellectual puzzle box.
Okay, I see where he's going with this. He's applying that to physics.
Precisely. He suggests physics was becoming like that deliberately obscure, only understood by the initiates, like you needed a special key to unlock Góngora's poems. And he felt this trend ought to be opposed, strongly.
So the takeaway is that complexity isn't always depth, right? Sometimes jargon or overly complex explanations can just be barriers. They can isolate knowledge.
Yeah, it makes you ask, is this concept genuinely deep? Or is it just hard to understand because of the way it's presented? Maybe a kind of intellectual gatekeeping.
And he connects this back to our role in history. He says, while we're products of history, we also shape what comes next. It depends on our stopping to think and acting according to reason, whether there will be decay or a new rise after the crisis.
It's an active choice, then, to keep things clear, accessible.
Right. Not just let things drift into obscurity. And to really hammer home this point about historical amnesia, he shares some, frankly, shocking anecdotes.
Oh, yeah. Like what?
He mentions his friend, Professor Hans Thüring, who wrote a book where he wasn't sure whether chemistry really started with Lavoisier around 1780, or maybe Dalton in 1808.
Okay.
And for physics, Thüring dated its beginning to Newton's Principia in 1687. He sort of acknowledged Archimedes discovered some physics laws way back around 250 BC, but said his discoveries can hardly be called the real beginning of physics.
Dismissing Archimedes. Wow. Levers, buoyancy, that's fundamental stuff.
Exactly. And Schrödinger then lists some of these supposedly insignificant discoveries from that Greek era, like inferring probably from Aristarchus's heliocentric ideas that the fixed stars must be at least 2 light years away.
2 light years in 250 BC. How?
Pure reason and observation. It's an astonishingly good order of magnitude guess. And the follow-up conclusion. From that distance, our sun would look like just another faint star, meaning many stars must be as big or bright as the sun, or even bigger.
That's incredible deduction. Over 2,000 years ago.
Mind-blowing, isn't it? And he throws in another story, this one from Charles Darwin's Voyage of a Naturalist.
Okay.
Darwin noted that in 1888, the educated folks in Argentina were apparently sensationally surprised to learn the Earth is a sphere.
Wait, in 1888, people didn't know the Earth was round. That knowledge was ancient.
Over 2,300 years old by then. Since the Greeks, like Eratosthenes, measured it. It really shows how easily fundamental knowledge can be lost or just fail to spread through culture.
Yeah, these examples really drive home Schrödinger's point about forgetting the past, right? It's not just about trivia. It's about losing the lineage, the context that gives our current knowledge its real weight.
Exactly. And prevents it from becoming that mysticism and superstition Farrington warned about. If you forget the why behind an idea, you just accept the what blindly.
Okay, so after laying out all these broader concerns, historical amnesia, gongorism, the cultural context, Schrödinger finally brings it all back to quantum mechanics. This is where he drops his heretical view.
Right. He connects the cultural critique directly to the physics. He confesses his view that quantum jumps are the modern counterpart in physical theory to the old theory of epicycles.
Epicycles, okay. Refresh my memory on this. Astronomy, right. Complex circle.
That's the one. Developed by the ancient Greeks, perfected by Ptolemy. To explain how planets seem to wander erratically across the sky, they imagine planets moving in small circles called epicycles.
Uh-huh.
And the centers of those circles moved along larger circles called deferents around the Earth. It was incredibly ingenious, mathematically complex, and it actually worked remarkably well for predicting where planets would appear.
So it made good predictions.
Astonishingly good for its time. It was the standard model for over 1,400 years. But eventually, it got replaced by the simpler, more fundamental, heliocentric model planets orbiting the Sun.
Okay, so Schrödinger is saying quantum jumps are like epicycles.
Exactly. He sees them as a clever, maybe even necessary descriptive tool, a way to account for observed phenomena, like those discrete spectral lines. But, like epicycles, he suspects they aren't the fundamental reality. They might be a kind of mathematical fiction that's hiding a deeper, smoother, more continuous truth about how atoms actually work.
Wow. That's a really provocative analogy. Okay, so let's dive into the quantum revolution itself and see where he thinks things went astray with these jumps.
Right. The story really kicks off with Max Planck in 1900, his discovery, which came from pretty abstract theoretical work on radiation.
So black body radiation, wasn't it?
Exactly. He found this totally unexpected discontinuity right where you'd least expect it, in how energy is exchanged between matter, like atoms, and radiation, like light or heat. It wasn't a smooth flow. It came in these discrete packets, or quanta.
The birth of quantum theory.
Pretty much. But Planck himself was actually quite reluctant at first to take the next logical step.
Which was?
The idea that atoms themselves could only exist in specific discrete states with fixed energy levels. Or that radiation itself was fundamentally divided into these photons. He was cautious. It completely broke with classical physics.
Understandable. But then Einstein came along.
Yes, just a few years later, 1905. Einstein, with incredible insight, proposed light quanta, photons, backing it up with what Schrödinger calls irresistible arguments based on the photoelectric effect.
We'll probably come back to that one.
Oh, definitely. Then, Niels Bohr, in 1913, really ran with Planck's core idea. He took the discrete states of atoms seriously and built this ingenious model.
The Bohr model of the atom, electron orbits.
Right. And it brilliantly explained atomic line spectra, those specific colors of light atoms emit or absorb. That turned spectra into irrevocable direct evidence for discrete states. Bohr's theory was hugely successful for about a dozen years, explaining so much. Schrödinger calls it a grand series of such marvelous and genuine successes.
There's always a but, isn't there?
There is. Despite all its triumphs, Bohr's theory had this critical, you might say glaring conceptual hole.
Which was?
He could describe the atom when it was just sitting there, stable, in one of its stationary states. But it was completely silent about the periods of transition or quantum jumps themselves.
It couldn't explain the jump itself.
Not at all. And because the theory disallowed any intermediary states, the atom couldn't be between levels, these transitions had to be seen as instantaneous. Poof. It just leaps.
Okay, I see the problem. Instantaneous leaps. That feels weird.
It felt weird to Schrödinger, too, and contradictory. Think about it. An atom emits light, right? Sometimes that light forms a coherent wave train, like a ripple, that can be measured in experiments maybe 3 or 4 feet long.
Yeah.
Well, creating a wave train takes time. A wave doesn't just appear instantly. But the instantaneous jump idea left literally no time for the atom to do anything, let alone radiate a continuous wave. It was supposed to be in a stationary state, then instantly in another.
So how could it radiate a wave that takes time to form?
Exactly. That's the contradiction. How could the theory be so good at predicting the discrete results, the spectral lines, but completely fail, even contradict itself when it came to the process of change? It was a major conceptual gap.
Okay, so that sets up the need for something better. Wave mechanics enters the picture.
Right. Schrödinger explains that wave mechanics provided a new description of the states. And this is really crucial for understanding his viewpoint. The previously admitted discontinuity was not abandoned, but it shifted from the states to something else.
Shifted to what?
He uses this great analogy. Think of something that vibrates naturally, a guitar string, a drum skin, maybe a bell tolling.
Okay.
When you strike a bell, it doesn't just make one pure flat tone forever.
Right.
It rings, it shimmers, it vibrates in complex ways. But mathematically, you can break down that complex vibration into a sum, a superposition of simpler, distinct vibrations.
Harmonics and overtones.
Exactly. These are called its proper vibrations, and each one has a very specific, definite frequency. These frequencies are characteristic of the bell itself. They're discrete. You get the fundamental note, the octave, maybe a fifth, but you don't get frequencies in between those specific proper modes.
Got it. Discrete frequencies from a continuous vibration.
Precisely. And the huge breakthrough of wave mechanics was finding a way to model atoms where Bohr's stationary states became like these proper vibrations of some underlying continuous wave.
Ah, so the states are like the allowed notes on the bell.
Kind of. And the discrete energy levels associated with Bohr's states became the discrete proper frequencies of these atomic vibrations. It just fell out of the math naturally. And even better, the frequencies of light actually observed in spectra turned out to be simply the differences between these proper frequencies.
Differences, how does that work?
Well, if you have two or more of these proper vibrations happening simultaneously, superposition. Again, their interaction naturally produces frequencies corresponding to their differences. It provides a mechanism for generating those specific spectral lines without needing an instantaneous jump between separate states.
So the discreteness is still there, but it's in the frequencies, not in the states being totally separate things you jump between.
That's the core idea. Wave mechanics keeps the necessary discreteness but embeds it within a continuous wave process.
Okay, this is starting to make sense. So Schrodinger argues this fundamentally changes how we should even think about stationary states.
Absolutely. He says the principle of superposition not only bridges the gaps between the stationary states, but it completely does away with the prerogative of the stationary states. The epithet stationary has become obsolete.
Obsolete? Why obsolete?
Because if you just learned wave mechanics from scratch, without knowing about Bohr's earlier model, you'd never think the atom somehow prefers to be in only one of its proper modes at a time. Superposition is natural things can be in combinations of states.
But we still talk about energy levels, transitions, probabilities.
Exactly. Schrodinger points out that using that old language, energy levels, transition probabilities, keeps dragging us back to the old, misleading picture of separate states and jumps. It's like the language itself is trapping our thinking.
Linguistic inertia, you called it?
Yeah, the words shape the thoughts. He felt the language was obscuring the continuous wave reality that the math was pointing to.
And this leads him to question how we think about energy itself at this level, right? The whole energy parcel idea.
Right. We have this ingrained habit, he says, of thinking of Planck's constant H-times of frequency as this literal bundle of energy that one system loses and another one gains, like passing a tiny package back and forth.
Seems intuitive, maybe. Conservation of energy.
It seems intuitive, but Schrödinger argues it's not the only way to account for the precise energy bookkeeping in nature, his radical claim. I maintain that it can, in all cases, be understood as a resonance phenomenon.
Resonance again. So forget energy parcels. Think resonance.
That's his proposal. Ought at least to try and look upon atomic frequencies just as frequencies and drop the idea of energy parcels. And to make this clear, he makes this really important distinction between two meanings of energy.
Two meanings. Okay.
Macroscopic energy, the kind we measure in bulk, like heat or electricity, he calls a quantity concept. Quantity is gross. It's about how much.
Makes sense. Joules, calories, kilowatt hours?
Right. But microscopic energy, the ASHI associated with a single interaction or photon, he suggests thinking of differently. He calls it a quality concept or intensity concept. Intensitätsgröße.
Quality or intensity. How so?
Think of it less like an amount to be transferred and more like a grade or vibrancy. High-frequency UV light has high-grade energy due to its rapid vibration. Low-frequency radio waves have low-grade energy. It's about the nature of the vibration, its quality, not just a packet size.
So high frequency means high quality, low frequency means low quality.
Sort of. And while you get macroscopic energy by summing up contributions across frequencies, and H is involved, he argues this does not necessarily entail that in every single case of microscopic interaction, a whole portion He of macroscopic energy is exchanged.
So the connection between microscopic frequency and macroscopic energy doesn't force us to think of little packets being swapped in every single interaction.
That's his point.
Yeah.
He believes we can view microscopic interaction as a continuous phenomenon based on resonance without messing up the established results of Planck and Einstein about overall energy balance. It's a fundamental shift from discrete packets to qualities of continuous waves interacting through resonance.
Okay, so if it's all about resonance, what's the mechanism? He mentions the wave equation.
Yes. He says the inalienable consequence of the wave equation, as used everywhere, is that the interaction between two microscopic physical systems is controlled by a peculiar law of resonance.
And he gives an equation for that.
He does. It's elegant.
Yeah.
V1, V1 equals V2, V2.
Okay, break that down. V is frequency.
Right. So the difference between two proper frequencies, V1 and V1 in the first system, must equal the difference between two proper frequencies, V2 and V2, in the second system, for them to interact strongly.
Like tuning forks. If the difference in pitch on one matches the difference on the other, they resonate.
That's a great way to think about it. It's about matching frequency differences. And this is where he slams the obsolete interpretation.
The energy parcel view.
Yeah. He says taking that resonance equation, multiplying everything by h, and then saying, aha, system 1 dropped from energy HV1 to HV1, and system 2 gained that energy, going from HV2 to HV2. He says that interpretation is obsolete.
Why obsolete?
He says there's nothing to recommend it, and it bars the understanding of what is actually going on. Because wave mechanics, with superposition, allows for simultaneous gradual changes of any and all amplitudes. The waves corresponding to different frequencies can smoothly grow or shrink.
So the energy transfer can be gradual, mediated by this resonance, rather than an instant jump.
That's the picture he's painting. You keep the discrete frequencies, which are essential, but the change between states becomes a continuous process of shifting wave amplitudes driven by resonance.
And this resonance idea works for more than two systems.
Yes, he knows it can involve 3 or more systems interacting with the frequency differences balancing out. And if you treat multiple systems as one big system, the frequencies just add up simply, like V1 plus V2 equal V1 plus V2. It's just this very interconnected, continuous interplay.
Okay. He even makes a joke about this additivity, right? The cigarettes.
Yes, the cigarette analogy. If I smoke 25 cigarettes per day and my wife smokes 10 and my daughter 12 is not the family consumption, 47 per day on the average.
Right. Just a common sense way to say adding things up isn't weird, even if the individual acts aren't simple exchanges.
Exactly. It's a touch of humor to make the point that thinking in terms of combined effects or sums, like frequencies, is perfectly natural, perhaps more natural than imagining discrete parcel exchanges for every interaction.
Okay, so he's built this alternative picture based on waves and resonance. Now, how does he apply it to actual experiments, the ones that supposedly prove the energy parcel view?
Right. He tackles the blatant evidence head-on. A classic example is the Frank-Hertz experiment.
Okay, what happens in that one?
You shoot a beam of electrons, cathode rays, through a gas vapor like sodium vapor. Then you use an electric field to measure the electron's speed after they've gone through the vapor. And you also look for any light the vapor emits.
And what do you see?
What you typically see is, well, pretty striking. If the electrons start slow, nothing much happens. No light, electrons keep their speed. But once the initial electron speed hits a very specific threshold, bang, 2 things happen at once. The vapor starts glowing, emitting light at a very specific frequency, and the electron beam splits. Some electrons keep going at the original speed, but others are now moving slower, and the energy they seem to have lost is exactly equal to h times the frequency of the emitted light, hv.
Ah, okay. Looks exactly like the electron gave a packet of energy hv to the atom, which then emitted it as light.
Precisely. And if you crank up the initial electron speed even more, you see electrons losing 2 packets, 2 HV, or 3 packets, 3 HV, and so on. It really looks like direct proof of discrete energy levels and quantized energy exchange. It's been a textbook example for decades.
But Schrödinger says no.
He says, but it is just as easily understood from the resonance point of view, and maybe more consistently.
How? How does resonance explain that?
Okay, think wave mechanically again. The electron beam isn't just particles, it's a monochromatic beam of de Broglie waves. Waves with a specific frequency related to the electron's velocity.
Right, particles or waves.
Resonance occurs when the frequency of this incoming electron wave, let's call it V1, hits a point where it relates properly to the frequency difference between 2 states in the atom, say V2, V2. Specifically when the electron's energy HV1 is enough to potentially excite the atom.
Okay.
At that resonance point, a new de Broglie wave frequency, V1L, appears for the electrons corresponding to the slower speed, and simultaneously, the atoms start vibrating and emitting light at the frequency, V2, V2. It's a coupled resonance phenomenon.
And the splitting of the beam, where some electrons lose energy and some don't.
That's explained by how waves behave in the electric field used for measurement. De Broglie's wave equation shows that an electric field acts like a medium with a refractive index that depends on the wave's frequency. So the field naturally bends or separates the waves corresponding to the original frequency, V1, and the new lower frequency, V1.
Like a prism splitting light.
Exactly like that. It's a natural consequence of wave propagation in that field. Even more complex interactions, like energy transfer to other gas molecules without light, impacts of the second kind, he argues, fit the resonance picture if you consistently treat everything involved as waves.
So the key takeaway is that the experiment doesn't force the jump parcel interpretation. The wave resonance view explains the same observations, maybe even more naturally, by explaining the beam splitting via wave optics.
That's Schrödinger's argument. He says the separation of frequencies is nothing enigmatic. It's just basic wave physics from de Broglie's work. And crucially, this wave picture implies gradual, continuous processes, not instantaneous jumps.
Okay. What about chemistry? Can resonance explain chemical reactions?
He tackles ordinary chemistry, too. Take hydrogen and oxygen reacting to form water, maybe triggered by UV light. You see water droplets forming, separating out.
Right. How does the wave picture handle that?
Well, wave mechanically, the initial H2 and O2 gas mixture isn't just particles bouncing around. It's represented by a complex superposition of vibrations of the whole combined system, translational, rotational, electronic modes, everything.
Okay, a complex vibration.
As the reaction happens, the specific vibrations corresponding to H2O molecules don't suddenly appear. Schrödinger says they gradually chime in. Then, as droplets form, a third group of vibrations, characteristic of the liquid state, also chimes in. It's like an orchestra where new instruments gradually join the symphony.
A continuous evolution of the overall vibration pattern.
Yes. But here, he makes a critical, almost frustrated point. He complains that wave mechanics, while offering this conceptually coherent picture, isn't yet powerful enough analytically to actually calculate the details of this macroscopic process.
So math is too hard.
Essentially. But then he contrasts this with the traditional interpretation, which, he says sarcastically, gives ample information about a host of experiments that nobody's ever been or ever will be able to perform.
Like what?
Like telling you the exact probability of finding an electron at a specific point inside a hydrogen atom, if you could somehow look there. He sees this as providing answers to unaskable questions, creating a false sense of detailed knowledge about unobservable microevents.
So the standard view gives precise answers for things you can't actually measure, while the wave view struggles with the math for things you can see, like water forming.
That's his critique. He finds the traditional picture, this picturesque pageantry of individual molecules swallowing or respuing whole energy parcels being disrupted and recombined, to be simply wrong. He thinks it actively hampers further progress because people mistake this convenient picture for the actual reality.
But chemical equations, diagrams of molecules, they're useful, right?
Oh, absolutely. He acknowledges they are useful, nay, indispensable conceptual shorthand. They work brilliantly for organizing chemical knowledge and predicting reactions. They are the famous as if.
As if things happen that way.
Exactly. The shorthand looks like it describes the single microevent, the individual molecular collision, but is wrong in this. It's a powerful tool for macroscopic prediction, but it shouldn't be mistaken for a literal description of the underlying continuous wave mechanical dance. Don't confuse the map with the territory.
Okay, let's tackle another big one. The photoelectric effect. This was huge for Einstein and the photon idea, right? The instant ejection of electrons.
Absolutely, a cornerstone. The key observation that baffled classical physics was that electrons pop out of a metal immediately when you shine light of high enough frequency on it, no delay, even if the light is incredibly faint.
And classical waves should take time to build up enough energy to kick an electron out.
Right. Classical theory predicted maybe half an hour delay for weak light. So this instantaneous effect looked like slam dunk evidence for light arriving in packets, photons, that delivered their energy all at once to an electron, causing an instantaneous jump.
Makes sense. How does the standard quantum view explain it now?
The orthodox view uses probability. It says the incoming light instantly gives every electron a tiny, tiny probability of making a leap to a higher energy state, escaping the metal, in the next fraction of a second. Since there are billions of electrons, a small fraction do leap immediately, explaining why we see electrons right away.
Okay, a probabilistic explanation for the apparent instantaneity.
But Schrödinger asks, is this necessary? He points out that wave mechanics itself also predicts the immediate appearance of electron waves. He says the math does produce without delay electronic wave trains of the higher frequency that we observe emerging from the metal. Remember, observing the electron's frequency is observing its velocity or energy in wave mechanics.
So the wave equation itself predicts immediate electron waves.
Yes. So he asks pointedly, after this has been recognized, is the probability scheme any longer needed? Has the idea of the mysterious sudden leaps of single electrons not become gratuitous? Is it expedient? Why add this extra layer of probabilistic leaps if the fundamental wave equation already accounts for the observation?
And he points to electron diffraction experiments.
Exactly. Like G.P. Thompson's experiments showing electrons behaving like waves, creating interference patterns. He says the waves are there anyhow, and we are not at a loss to prove it. The wave nature is experimentally verified, so why cling to the leap idea when the wave picture works?
It feels like he's constantly saying, the wave picture is more fundamental, more consistent. Let's stick with that.
That's the core of his argument across all these examples.
Okay, let's shift to the mathematical consistency arguments. He felt the whole sharp energy states and jumps scheme wasn't just conceptually problematic, but mathematically shaky too.
Yes, he saw a deep inconsistency there. He points out this certain danger when convenient shorthand-like picturing systems and sharp energy levels making abrupt transitions gets mistaken for the actual reality. It's about how language shapes thought again.
The power of words.
He puts it beautifully. In the inseparable union of speech and thought, the primacy, rather paradoxically, rests with speech. When we hear terms like energy level and quantum jump used constantly, pronounced with authority, we forget they might just be abbreviations or models. We are induced to believe that they describe a reality.
And this applies beyond physics, obviously.
Oh, absolutely. Anywhere simplified models become dogma. But specifically in quantum mechanics, he argues the scheme of sharp states and jumps is inconsistent with the underlying math.
How so? Beyond the mystery of the jump itself.
It's about how interactions are handled. When two systems interact, it becomes unclear which set of pure energy levels even applies. Physicists use a mathematical artifice, he says. They split the total energy into parts for the isolated systems, plus an interaction energy treated as a small disturbance, a perturbation.
Standard technique, right? Perturbation theory. Standard, yes. But Schrödinger digs into what the calculation actually tells us. The math gives you small changes in the amplitudes of various possible states over time. This result is then interpreted as the probability of transition between just one initial and one final state.
But that's not what the math says.
No, he insists. The computation does not give this result. What it actually shows is that the interaction causes a host of pure energy states to be superposed. The system evolves into a complex mixture, a blend of many possibilities according to the wave equation.
But the interpretation jumps to a single outcome.
Yes. Physicists choose to interpret this complex superposition as meaning a complete, instantaneous jump between just one specific pair of states that satisfy the resonance condition. He sees this as a massive leap of interpretation, ignoring what the wave function itself is saying about continuous evolution and superposition.
Okay, that's a really sharp critique of the standard interpretation of the math.
And it leads to this fundamental contradiction he points out. If you start by assuming two systems are in pure energy states and then let them interact.
That interaction, however weak, immediately creates a strong mutual influence. It slightly distunes the systems. What were pure single-frequency modes in isolation are no longer pure modes in the combined interacting system. The combined system is suddenly a complex superposition, very far from finding itself in one of its proper modes.
And that complex state is why things change.
Precisely. That's the very reason why, as time goes on, anything will happen at all. An isolated system perfectly in one pure mode would just stay that way forever, no change. Interaction inherently creates a mixed state that then evolves.
So the picture of stable atoms in pure states just bumping into each other is wrong.
He says it contradicts the fundamental concepts of the theory. His conclusion is stark. Where anything happens, we are not facing pure energy states, so obviously we never are. The whole setup of starting with pure states before interaction is fundamentally flawed, self-contradictory.
Wow, okay. So the standard picture is built on a foundation he sees as inconsistent with the theory itself.
That's his claim. It's a powerful challenge to the conceptual framework.
And he connects this back to the bigger picture, the cultural aspect.
Yes, he argues that even if physicists find this shorthand convenient among themselves, these ideas eventually filter out into the broader culture, into our world picture.
And people outside physics care about these fundamental questions.
Deeply. He says, many of our educated contemporaries are yet deeply concerned with many general questions. One of the most stirring among them certainly is whether actually natro tacit saltus or no. Does nature take leaps, or is it continuous?
It's a basic philosophical question about reality.
Exactly. So physicists must be careful not to veil or distort the implications of their theories by indulging in loose speech or flawed metaphors. He wonders if our scientific papers will be as clear and enduring as Archimedes' work in 2,000 years, or just obscure texts needing commentators.
Because science is not a soliloquy?
It gains value only within its cultural milieu, a powerful plea for clarity and intellectual honesty.
Okay, let's get even more technical for a moment. He had specific issues with how collision problems are handled mathematically.
He did. He doubted whether you're even allowed mathematically to start a collision problem by assuming the incoming particles are in pure energy states. He noted this common procedure gives okay results in the first approximation, but leads to entirely unacceptable ones in the next step.
Suggesting the starting assumption is flawed.
Yes, and the core mathematical reason, he points out, is that the term in the wave equation describing the interaction must be nonlinear.
Nonlinear. Okay, unpack that a bit. What does nonlinear mean here, and why does it matter?
Okay, think simple. Linear means double the cause, double the effect. Simple superposition works. Nonlinear means the effects don't just add up simply. Interactions can amplify or interfere in complex ways. Two waves interacting might produce something totally different from just the sum of the two waves.
An interaction has to be nonlinear.
Yes, he says it must contain the product of the two wave functions, otherwise it could not entail any interaction between them. This nonlinearity is essential for interaction, but it messes up the simple picture of superposition. It means the whole is not just the sum of the parts when systems interact.
And what are the consequences of this nonlinearity?
Well, first, the initial small change calculated by perturbation theory might still be okay. But crucially, second, you can't just add up the effects of multiple interactions independently. They influence each other significantly. And third, getting better approximations beyond the first step becomes mathematically very intricate. But the standard methods often treat it like a linear problem, which is insufficient.
He had an example from his own work, right? The Stark effect.
Yes, his 1926 calculation of how hydrogen spectral lines split in an electric field. The first approximation looked great, matched experiments well. But later work by Lanczos showed a deeper issue.
What was the issue?
The assumption that the external electric field was always weak compared to the atom's internal field wasn't quite right. Further from the nucleus, the external field becomes relatively stronger. This subtle effect, missed by the linear approximation, means the Stark lines aren't perfectly sharp. They have a tiny inherent broadening.
So the simple approximation hit a continuous effect.
Exactly. It shows how relying on these approximations can mask the underlying continuous reality that a full nonlinear treatment might reveal.
He also had issues with picturing particles approaching each other.
Yes, back to the conceptual problem with pure states. If you represent a particle moving with fixed velocity as a pure energy state, wave mechanically, that's a plane wave filling all of space.
A wave everywhere.
Right. So if you have two such plane waves representing two particles, they overlap everywhere. There's no feature representing distance from each other. The state already includes all possible distances, including close ones where interaction is strong.
So starting a collision calculation with these plane waves ignores the whole process of them actually getting closer and the interaction gradually turning on.
Precisely. It disregards the building up of the interaction during the gradual approach. He finds it surprising the method works as well as it does, given this conceptual shortcut. He uses an analogy from classical optics by Sommerfeld.
The light wave entering a dielectric.
Yeah. Sommerfeld found the very front of the wave doesn't refract according to the simple Snell's law, because the electrons in the material need time to be gradually rocked into oscillations before the steady-state refraction happens. You can't use simple perturbation theory for that initial gradual buildup.
And Schrödinger thinks quantum mechanics shouldn't magically bypass these kinds of gradual processes.
Exactly. He finds it hard to believe that quantum physics holds the master key for overcoming these intricacies without attacking them. The standard method just assumes the interaction turns on instantly and calculates the probability of hopping, ignoring the potentially crucial continuous buildup phase.
This ties into his critique of that neo-Machian purism, doesn't it? The idea that only predictions matter, not the underlying picture or even the correctness of the math.
Absolutely. Mach's philosophy basically said science just needs to predict future observations from past ones. Who cares if the model makes sense or the math is technically perfect as long as it works?
A very pragmatic view.
Maybe too pragmatic. Schrodinger asks, okay, if prediction is all that matters, why not by false mathematics? Nobody would agree to that. Why?
Because science needs to be consistent, self-correcting.
Right. He argues science isn't just a bag of tricks. It's an intricately connected and interwoven scheme. We rely on basic assumptions and logical deduction. Only a self-consistent scheme of correct mathematics can hope to handle unforeseen future observations and build a coherent understanding. Correct mathematics is the indispensable guide, even for the pragmatist. Most scientists do use models and seek understanding, not just prediction.
Okay. He also questioned the idea of integer numbers of particles from sharp energy states.
Yes. The idea that a system is in exactly one energy state implies it has exactly an integer number of particles, like one electron, or exactly n photons. He argues this is inadequate for real systems, like a gas.
What's his alternative?
A real gas, or any real system, should be represented by a superposition of proper modes with a considerable spread over many integers. We never experiment with exactly one particle. There's always some uncertainty, best described by a wave function spread over possibilities.
So those thought experiments about one electron doing weird things.
He finds the consequences ridiculous, like the idea of a spherical wave for one electron instantly collapsing everywhere when detected at one point. He argues if the number of particles isn't certain to be 1, maybe it's 0, 2, or 3, detecting one doesn't magically eliminate the possibility of others.
And he insists we need the wave picture to be real.
Absolutely. We sorely need those spherical waves as realities, not merely as expressing our lack of knowledge, to explain real experiments like electron diffraction. The wave has to be physically real and spread out to interfere with itself.
Which brings us right back to those particle tracks. Cloud chambers, photographic emulsions. They look so much like single particles leaving trails causing discrete events. How does he square that with the wave view? Isn't that direct evidence of jumps and particles?
This is the toughest challenge, and he acknowledges it. He first notes that we're usually looking at these records after the fact. We aren't really experimenting on a single particle in the sense of controlling and repeating the event under varied conditions.
Okay, but the tracks are there. They look like particles.
They do, but he insists these records certainly do not show us the transformation of a couple of plane waves into a number of other plane waves. The wave picture doesn't easily map onto these localized tracks. His opponent, he says, would argue, see, the waves aren't real. They just tell you the probability of finding a particle.
The standard Copenhagen interpolation, more or less.
Right. But Schrödinger pushes back. We have other experiments, like interference, that we simply cannot account for without taking the wave to be a wave acting simultaneously throughout the region over which it spreads. It can't be just probability.
So what's the real difficulty with the tracks for his wave view?
It's the exact balance of energy and momentum in the single event. You see an alpha particle travel a certain distance, create a specific number of ions along its track, and then stop. It looks exactly like it's handing over discrete packets of energy until it runs out. How does a continuous wave do that?
Yeah, how?
His explanation is, well, it's more speculative here. He suggests it happens in an adiabatic fashion, like a particle slowing down gradually in a field, not through sudden jerky stops. The particle's wave group maybe has its constituent wavelengths slowly, adiabatically increased so that the group keeps together, but effectively slows down.
A continuous slowing process rather than discrete energy transfers.
That's the idea. He urges us to shake off the nightmare that physical events consist in continual sequences of little fits and jerks. Even dramatic events like stars in emulsions, nuclear disintegrations, could, in principle, be slow, adiabatic processes on the timescale of the incredibly high frequencies involved.
But what are the particles then, if not little billiard balls?
That's the momentous question. He admits they aren't durable little things with individuality. His best guess, maybe they are like white crests in a choppy sea, temporary localized features emerging from the underlying continuous wave field. The wave is fundamental, the particle is an appearance.
And he uses von Lau's work on diffraction to argue the wave reality is indispensable.
Yes, von Lau showed conclusively that you need to treat X-rays and electrons as real waves to understand diffraction patterns. Schrödinger emphasizes that real here means the wave acts simultaneously throughout the whole region it covers. Otherwise, interference wouldn't happen.
It comes down to this fundamental difference, both and versus either or.
Exactly. Et-at versus out-out. Is the wave real and spread out, acting everywhere at once, both here and there to interfere? Or is it just a probability calculation for finding a particle which is either here or there?
And he argues the either-or view simplifies the particle tracks but loses everything else.
Yes. He says if you take the probability view, either or, The single event observation becomes comparatively easy to tackle, but all the rest of physics, unfashionable at the moment, is lost to sight. Things like interference become inexplicable if the wave isn't truly real and extended. He ends by challenging anyone to dispute this discrepancy away. It's a stark choice he presents.
So wrapping this up, we've really gone deep into Schrödinger's challenge here. He wasn't just tweaking quantum mechanics. He was arguing for a completely different way of seeing the microscopic world, continuous waves, resonance, no jumps.
And it wasn't just physics. It was a critique of scientific language, of forgetting history, of potentially sacrificing conceptual coherence for predictive convenience. The quantum jump, for him, was this prime example of a useful shorthand, maybe, but one that had solidified into a misleading dogma, a gongorism obscuring the underlying reality.
He really championed consistency, the reality of waves, and science staying connected to its cultural context, communicating clearly.
Absolutely. His whole essay is a call for that kind of intellectual honesty and clarity.
And for you, the listener, this deep dive really shows how even foundational ideas in science aren't set in stone. They can be questioned, reevaluated, even by the giants who helped build them. It forces us to ask why we believe what we believe.
Right. It's a masterclass in critical thinking, in questioning assumptions, in seeing ideas within their historical and philosophical context. Schrödinger's journey shows that sometimes the deepest insights come from being willing to challenge that milk of the mother's milk, the things everyone else takes for granted.
So the next time you hear about a quantum leap, or maybe any big breakthrough, what questions will you ask? Will you wonder about the how and the why, and maybe whether it's truly a leap or perhaps part of a more continuous resonating wave of change?
Thinking about science today, with its incredible pace, it brings Schrödinger's final concern right back to us, doesn't it? In 2,000 years, will our scientific understanding be transparent, like Archimedes' work still is? Or will it have become so specialized, so laden with its own gongorisms that its essence is lost to all but a few, disconnected from the broader culture it's meant to enlighten? It's a profound thought about the legacy we're creating.